Okay. Can ignore the thing about moment of inertia, about the center, but we have a circle of radius 4 centered at the point 1, 2. We want to find the mass in a circular lamina of this dimension if the density function is x squared plus y squared minus 2x minus 4y plus 5. Now, before we get into it, I chose to recognize that this density function is actually symmetric about the point 1, 2, because if you complete the square on the x terms, you get x minus 1 quantity squared. Completing the square on the y terms, you get a y minus 2 quantity squared. And then you have to subtract a 1 and a 5 because of the squares of these numbers. And that obliterates the plus 5 you have there. So this is the same as this. If you expand this, in other words, you're going to get this. And completing the square is a standard technique from pre-calculus. And was used, you know, it's used in your calculus course. And everybody's had the calculus course. So that should be pretty straightforward. Okay. Now what we do is, as usual, we think of partitioning one axis or the other, and we chose to partition the x-axis since it really doesn't matter which. And no, that's all right, that's right. Okay, the x values, well, circle centered at 1, radius is 4, the furthest left you can go is from 1, 4 units to the left is -3, from 1, 4 units to the right is 5. So you partition the x interval from -3 to 5, and you have a sample point within that interval, indicating by the purple line. And the length of the y interval that you're going to partition. The length of the purple line can be found by simple geometry. You have a triangle from here to here to here and up, and a similar triangle down here. Both triangles have dimensions such that the hypotenuse is 4, the one leg is x minus 4, and the other leg is going to be then the square root of this squared minus this squared. Square root of 16 minus the quantity x minus 1 squared. Where is it? Then this purple line, the line corresponding to the sample point within your x interval, is going to go from x star, well, to 2 minus this square root to 2 plus the square root of 16 minus the quantity x star minus 1 quantity squared. So coordinates of this point are x star 2 plus the square root. Coordinates of this point are x star 2 minus the square root. And we conclude that the region is described by x values from -3 to 5. For any x value, y goes from 2 minus the square root of 16 minus quantity x minus 1 squared, this expression, to 2 plus that expression. So the limits on the integral and the limits on the integral are going to be obvious. Now we want to consider the typical increment in our integration, which is the increment of width delta x for our x partition, and then we partition this rectangle from y equals this coordinate to y equals this coordinate, and typical interval will be a yj star interval increment here. So it's an x star, a delta xi, a delta yj increment with sample point xi star, yj star. Now I've glossed over some details, but this should by now be a familiar process. So the area of this increment is delta xi by delta yj. Its density is rho star ij. Okay, I'm choosing to put a star on it because it is defined by the sample point. And ij because it's the ith interval of the x partition, and then the jth interval of the y partition that corresponds to the x partition. So it's rho ij star delta xi delta yj, the product of the area and the density. And that's your delta m star ij. I choose to call it delta m star ij. And then the rho star ij is just your density function, this function, evaluated at xi star yj star. Here we have it. So that's your mass increment. Now the total mass is the sum of all your mass increments. From I equals 1 to n, you have the n strips, vertical strips, corresponding to the x partition. And then from j equals 1 to m sub I, for every I, you have a partition of the y coordinates, of the corresponding y interval. So that'll be the sum from j equals 1 to m sub I, where m sub I is a number of intervals in your y partition for the ith x interval. And that'll be then of mij star. We can write that then as the same sum, but we can use this expression for the mij star. We write this one to indicate that this is what we get when we add up all the masses. This is what we get when we write out the expression for the mij star, mij star mass. Okay, then it gets a little more technical, and physicists often gloss over the technical aspects of the mathematics. So we'll go ahead and gloss over them now, but they're important, so I kind of recommend them. But I'm more into, I have far more education in mathematics than in physics. So that's my own prejudice. But I think these are important, and they certainly are when you get deep into physics. Okay, well then this gives us the integral. Now the x partitions, the ones that go from I equals 1 to n, run from -3 to 3. And I say the x partitions, the x intervals. We're partitioning x values from -3 to 5, and that's what this sum represents. In the limit then, as delta x and delta y approach 0 uniformly, this sum will become an integral from -3 to 5. And then for every I, we have a partition of a y interval. And that partition goes from j equals 1 to m sub I, as we've said. And the limits of that partition for any given x sub I are these. So there are the limits on the y interval, with the y integral. That's the integral. Now we just have to calculate the integral. I'm going to mention, and I didn't in class, that you can sort of visualize the density of this thing by visualizing a circle down in the plane. So we have an xy plane here, we have xyz axes, and we have this circle. The density at the center is 0, because of course at 1, 2, x equals 1, y equals 2, we get 0. You can verify that the density for any point on the rim of the circle is going to be 16. Also, a graph of this function is going to be a paraboloid of revolution. So that the values of the function range from 0 here to 16 here. So we have this paraboloid of revolution whose volume will be the same as this integral. So that the mass of this thing can be visualized as the volume of this paraboloid. Now if we had a cylinder of height 16 and radius 4, the area down here would be 16 pi, pi r squared, r is 4. The altitude would be 16. So if we do a cylinder here, the cylinder volume would be 16 times 16 pi, or 256 pi. If you look at the volume of this paraboloid of revolution versus the volume of the entire cylinder, you see that the volume ought to be more, half more or less of the volume of the cylinder. So that may be half of 256 pi, which would be 128 pi, which actually turns out to be correct. Now, in the next video, I'm going to do the integration. I'm going to demonstrate some integration technique in the process. And I've been over it a couple of times, and what I'm getting does not appear to be 228 pi, which is the right answer. So I still haven't figured out where the error is, so you can have fun trying to correct me, and I hope that you do. And I comment throughout the process of doing the integral on possible pitfalls. And I did find a couple of little errors, but I can't find a place where I ought to get pi out of that integral. I haven't thought that deeply about it, time constraints. But there we have the way you get the mass of the paraboloid, and the way you can kind of model it as the volume, the mass of the circular lamina, and how you can kind of visualize that in terms of a paraboloid of revolution.